So yeah, I'm going to talk about some work that I did on fault tolerance beyond foliation, and I will describe shortly what that means. And this was work that I did in collaboration with Hector, who's there in that picture, but also should thank the whole rest of the fault tolerance team at PsiQuantum, who've all contributed to these discussions. So this is really a talk about the relationship between codes and fault tolerance. Obviously, these are two very central parts of this field of quantum error correction, and they're related to each other. And the way I like to think about it is that a code is this static object. It's really just a description of parity checks, usually with stabilizer codes that operate on some set of qubits. It has some logical subspace where we can put logical information. But it doesn't, in of itself, do anything. It's just a description of a subspace. And fault tolerance, on the other hand, is the way that we can bring this code to life to actually do something with it. It's a description of the evolution of a code over time and how we can actually operate on it whilst maintaining those properties that allow us to do error correction. And generally speaking, if we're interested in doing quantum computing and we want to do logic and have that be fault tolerant, then fault tolerance is the thing that we're actually interested in. The code is almost irrelevant. It's really the ability to build this fault tolerant channel. But generally speaking, the way we get to fault tolerance is to start with a code and then use it and figure out some set of operations that we can do on it to build a fault tolerant scheme out of it. And this picture is representing the most standard example, which is to start with a square surface code and then make repeated measurements on it to build up a fault tolerant set of information. So this process, which I'm sure everyone here is familiar with, was described in this paper by Bolt and others a few years ago as foliation. So they were talking about the measurement-based setting. So this is this process of creating these repeating layers of a code, so repeatedly measuring the same set of parity checks to build up a fault-tolerant scheme. And then more recently, that's been shown that it can be also done for anything which doesn't need to be a CSS code by Ben Brown and Sam Roberts. So I Googled this, and it turns out it actually wasn't the quantum error correction community that came up with this first. The geologists got there before us. So this picture, I think, is actually a very nice representation of what foliation means for us as well. So it turns out there are these types of rocks. So there's a certain type of metamorphic rock that can form in different ways. So these are both made out of pretty much the same thing, but in a foliated rock, you have certain conditions of pressure that cause the thing to form in these layers that build up this kind of stripy-looking rock. So it's a 3D structure that's built out of these thin 2D layers. But there's also another kind of rock formation that's pretty much made out of the same thing, but which has a much more homogeneous structure. So still a 3D object, but with a kind of different composition. And this is what this talk is about, not rocks, really, but about the fault tolerance equivalent of this. So how can we get to this thing, the thing that we actually want in the end, the ability to get to fault tolerance, without needing to go through this process of repeated layers, so we can create the fault tolerance in maybe a more homogeneous way. So there's, I guess, a few aspects of that I want to go through. I want to talk about how we can construct this kind of fault tolerance scheme, specifically for things that are related to the surface code, how we can search through those to maybe find some things that are good in some way, so looking for things with higher thresholds. And then I want to share some kind of ideas about how that might look in a real system, so to bring it back to reality. But there's a few things that I kind of hope that you'll be able to take away at the end of the talk. So I think maybe the most important thing is that fault-tolerant channels are not codes, and actually when we start to think about fault tolerance, some of the properties that you can get to are counterintuitive if you started off thinking of a code that you then sort of move through time. And some of those things are kind of surprising, and ultimately the fault-tolerant channel is the thing that we want, and there are other ways of getting there that don't involve you starting first with a 2D code. The other thing is that self-duality isn't limited to the square surface code. Even in this class of surface code-like structures, there are other things that we can find. And also these things have a pretty promising high threshold performance, so certainly at least competitive with other schemes and maybe in certain regimes better. Okay, so this all starts with the surface code, and I don't need to introduce it because we've had a bunch of people already give a very nice introduction to this, have a bunch of qubits arranged on a square lattice, and the code is defined by a set of parity checks. There are two types of those, plaquettes and stars, or primal and dual, as I'll refer to them as. And we make this thing fault tolerant generally by making these repeated rounds of stabilizer measurement. So this is the picture that I guess is more usual to think about, where we start with a set of matter qubits and we're making operations on them in time. But there's this alternative picture in the measurement-based setting where instead of having physical qubits and making repeated operations, we instead create an entangled cluster state. So this is basically swapping out time and space. So we can create this 3D cluster state and then, after it's prepared, measure the qubits out one layer at a time, or actually in any order we want. And these two things are really exactly the same as each other, at least under many circumstances. So if the operations are ideal, they're exactly the same, they produce exactly the same set of syndrome information. The difference is really just in the ordering of the operations. So in the matter-based case, you're preparing qubits, you're doing entanglement and measurement, and you're interspersing multiple rounds of that, so repeated rounds of entanglement and measurement. Whereas in the measurement-based case, you do all of your entangling operations at the beginning, and then you make all the measurements. So as long as the procedure is not adaptive in any way, as long as you're not changing anything and you're just doing those fixed set of operations, there's really no difference between the two. So, I mean, this holds as well when you add errors. So if you have a phenomenological error model, it's still the case that these things are exactly the same. They have exactly the same thresholds and behavior. Obviously, if you talk about implementation details, so specific circuits, you can end up with differences between the two schemes, but just as you can if you change the gate error model with either one individually. And I think the clearest way, maybe, of seeing that these two things are doing the same thing in a very slightly different setting is this most important property, which is the thing we want, which is to create this fault-tolerant channel. And both of these things are doing that. They're really just some structure which is allowing us to take a code, in this case the surface code, and move it through either time or space. So in the case of the picture on the left, we're moving the code fault-tolerantly through time, and in the picture on the right, we're moving it through space. And with topological codes and the surface code, this property is the only thing you need to be able to get to a fault-tolerant logical gate set. Once we can create this channel, once we can create this fault-tolerant bulk, we can use that to do lattice surgery and whatever, all the other gates that we need to get to fault-tolerant computation rather than just a memory. So I think I've basically just told you that these two things are pretty much exactly the same. So why would we bother to think in the measurement-based case at all in that case? And I think it's the reason is, and particularly for the purposes of this talk, that it's often much more convenient to think in this setting of measurement-based when you're really thinking about everything that's laid out in space. Essentially, you're thinking about the whole space-time picture of the evolution of the code rather than thinking about a single time slice, and that often makes it much easier to see how you can reconfigure things and how you can move things around. So just as a kind of trivial example, if we have the cluster state, it's very easy to see that you can just rotate this thing in whatever direction you want, and I actually think that in Ben's talk yesterday we saw an example of this, of kind of moving through the state in a different direction. It's much harder to see how you could do that or how you would set up your set of operations to do that if you're thinking about physical qubits in space. I mean, you can kind of you could back it out from this picture, you would be able to rearrange them in some different way and do some different set of measurements. But it's much more intuitive to see that these things have to be exactly the same when you're thinking about the cluster state. And this is the reason that I'm going to use this framework for talking about the things here, because it's much more easy to see the geometric modifications that you can make to fault-tolerant schemes when you're thinking in this picture. But I do also want to emphasize that although I'm going to use the framework of measurement-based computation to describe these schemes because it's convenient, there's nothing about it that requires it to be built out of some circuitry that's actually measurement-based in practice, so you can map all these things back to some circuit model, and I'll show some examples of that at the end. Okay, so I'm not going to talk in detail about the construction of the cluster state. You can kind of see by eye that it looks very similar to the 2D surface code in layers, and you can kind of convince yourself by going through that all the stabilizers match up. But conveniently, you don't really need to understand the details of the structure of the cluster state, because there's a much simpler description of both of these things through what is called the syndrome graph, so a description of the relationship of the parity checks of the code. So this thing, or in this representation, the vertices represent the parity checks, so all of the parity checks of the code in the fault-tolerant picture, that is, are represented by vertices, and the edges represent the qubits. And this picture is obviously exactly the same for both of these two schemes, and it's a much simpler way of seeing the structure of what's going on. And if you extend the thing just beyond the syndrome graph to being a cell complex, so if we add faces and cells to that description, we get the whole description of the state, so of the primal as well as the dual. So this geometric structure, just having a cell complex, is really a complete description of the state, and we're going to be able to see everything we want to just from looking at that much simpler picture. So this isn't just limited to the square surface code, of course, which gave us this very symmetric cubic structure. But we can do the same thing for other structures as well. So here's another example, which starts with the hexagonal surface code. So this is really exactly the same thing, but with a modified geometry in 2D. And on the right, you can see the cluster state version of that, which basically the same as before, but with, again, a modified geometry. And these things have a syndrome graph that looks like this picture at the bottom. So it's basically just taking the geometry of the 2D surface code and extruding it up in the time direction. So the thing is made of these hexagonal prisms that are stacked in layers. So this is the general procedure that we follow. This is the procedure of foliation, where you take some 2D code, and in these case surface codes, and you extrude them up in the time direction to create this 3D fault-tolerant bulk. And this is generally the standard procedure that we take. We come up with some code, and then you apply these repeated parity measurements to create a fault-tolerant version of that code. But this is not the only way you can do it, and you can kind of see by eye, by looking at these things. We just said all we need is this cell complex to describe this structure, that you don't need to restrict yourself to something which is made up of these stacked layers. You can actually take any geometry and build a fault-tolerant scheme that goes on it. And so if we take some other random geometry, and you can see there's one of the cells is highlighted, and this thing has some unusual geometry to it, that there's no way of squashing that down so that the thing looks like parity measurements that are made repeatedly on a single structure of a 2D surface code. And you can see what it looks like if you define the cluster state on this. You're basically just wrapping this construction around the cells by putting qubits on every faces and qubits on every edge. Exactly the same construction that you use if you're building up the regular fault-tolerant cluster state. So the thing about this state is that it looks kind of unusual. It looks like a weird geometry. But really, it's exactly the same in almost every way as the surface code, apart from its geometry. So it inherits all of the behavior of the surface code. So it's the cells define the parity checks. We can do, because it has a syndrome graph structure, you can do decoding in exactly the same way. It's still a fault-tolerant channel that's taking a surface code from one point in space or time to another one. The logic gates are inherited. That's obviously important, because all we needed was this channel. You can still do lattice surgery or whatever other kind of gates you want in exactly the same way. And importantly, it can also be built with a 2D physical architecture. So although this is a 3D state, it can, and we've heard about this again from Ben yesterday, you don't need to build the whole thing at once. You can build it one layer at a time. And this is exactly what happens with the regular square surface code, and the same thing can be done here. Because the geometry is a little bit less symmetric, it's going to mean that somehow that's changing over time. It's not going to be the same set of qubits in every time slice, but it can still be built with a 2D architecture. Okay, so this is a basic construction that says, okay, we no longer need to restrict ourselves to looking at things which are defined just by a geometry in 2D. And instead, we have this big class of structures. We can now take any cellulation of space we like in 3D, and that's going to give us some fault-tolerant channel. So, I mean, that's kind of interesting, but really the reason you want to do that is to find some nice properties or something which is actually useful. And so the thing that we wanted to look for is to find something which had a higher threshold. Is the threshold that we get out of the cubic lattice from the square surface code, is that really the best you can do? Or are there any other geometries where you can get an improvement? I guess the difficulty with that question is, where do you start? There are infinite lists of these things, and if you go to Wikipedia, you can spend a very long time clicking through the different pages, looking at all of these crazy geometries. So what you need to do a reasonable search for that is to have some kind of intuition or some kind of clue about what it is about the structure of one of these geometries that is going to give it a good threshold or a bad threshold. And I think in general, this is not very well understood. In general, we don't have good ways of just looking at some set of parity checks and making a guess at whether it's going to have a good or a bad threshold. I think this is an interesting direction to try and understand more, especially as we try and engineer better codes. But with the surface code, with things that can be represented by a syndrome graph in particular, there is something that we can take as a clue, as a starting point to try and work in this direction. And it comes from the structure of the parity checks. So here is a picture of just a 2D surface code, again, just as a representation. And there's a parity check here. And if we see a parity check which is violated in the surface code, what that's telling us is probably one of those 4 qubits around it has suffered an error. Maybe it's 3, but probably it's 1. But the amount of information we're getting from that parity check depends on its geometry. So if we imagine having plaquettes of different sizes with different numbers of qubits on their boundaries, then we're getting different amounts of information. So if we have a hexagonal face, we're learning that 1 out of 6 qubits has an error, so that's kind of worse. We're not getting as localized information. If we have a triangular face, then we learn that only 1 out of 3 qubits. It seems better because it's more focused. We've got a more explicit piece of information about where the errors are likely to be. So this idea translates to the syndrome graph picture very nicely. So here's a picture of taking the plaquette and putting it on the syndrome graph. In the syndrome graph, that idea, the number of qubits that are incident on any parity check is given by the valence of the syndrome graph. And so here is a valence 6 syndrome graph as we go through these things. Okay, with a square one, we have a valence 4, so we have a bit more information. And the best case is with this triangular face where the thing has degree 3. So the intuition from this is that probably what we want to do is be looking for syndrome graphs that have a low valence, that have a low connectivity, and those are the things that probably the parity checks are more valuable, they're giving us more information. So this is a kind of hand-wavy thing, and we should check that this is actually maybe a meaningful metric. And so at this point, maybe the thing we're interested in the end is Pauli threshold. That's probably the things that most people are interested in. But it's very inconvenient to calculate Pauli thresholds. So these are, as probably a large fraction of the audience here knows, it's very time consuming to run these simulations and to set them up and to set up these different geometries. And what is much more convenient is to work out erasure thresholds. So the erasure channel just says that rather than have a bit flip or a phase flip at a certain location, I just have an error that I know exactly where it is. Or in another way of saying it, that a qubit is missing. And the erasure thresholds are much more convenient to work out because they just correspond to percolation thresholds, so there's no decoding needed. And even better, most of the time you can just look them up on Wikipedia because people have worked them out already for other purposes. So we can take these things and work out what the erasure thresholds are for a syndrome graph of different valence. And when you do that, what you see is that, this metric really is a very good predictor of how the threshold of that code is going to behave. So these things kind of follow this very nice curve. These are all graphs which are regular and have uniform valence. So this isn't always such a great metric, but in these cases, it works very well. And but I should say, I haven't yet said I can find codes like this. This is just saying if we're able to find a code that has this syndrome graph, then it's going to have this threshold against erasure. So I'm going to take this and try and construct some examples, and just with erasure for now, but later on we'll come back to the Pauli error to try and validate this statement that it's a good proxy, that erasure is a good proxy for Pauli error. Okay, so what we want to do is try and find some examples of codes that have low valence syndrome graphs. That's the game we're trying to play. But there's one more problem with that, which I haven't touched on yet, which is the duality problem. So kind of mentioned this at the beginning. Any one of these structures doesn't have just one syndrome graph, it has two. So it has one for the primal and one for the dual. So in the case of the square surface code, it just turns out that these two things are the same because the thing is self-dual. They both have a threshold of 25% against erasure in the fault-tolerant case. So we have a point that kind of sits here at the middle. This is our starting point and what we want to try and beat. But because the overall threshold is given by the lower of the thresholds of the two parts, we really need to get something which is higher than this in both the primal and the dual. So we want to move into the green region. Anything which is outside is overall going to be worse. And the problem is that if you have 2D surface codes, and many people I'm sure are aware of this, that as you try and improve in one basis, you make the other one worse. So here is the example of the hexagonal lattice, and in the one basis, the threshold has gone up, the valence of the syndrome graph is decreased, but in the other one, the threshold has gone in the opposite direction, so the valence is changed in the other direction, and that means that overall, we're worse off. The thing has got worse. And in fact, that this is true for any 2D surface code that you take. It's just a feature of the geometry. This has been known for a long time. And because of this, the square lattice is really the best you can possibly do if you're restricting yourself to 2D surface codes, because it's the only one which is self-dual. Okay, but we've now got this big other class of geometries that we can explore that aren't based off just 2D things that are extruded upwards. And so we can go to these lists on Wikipedia, we can search through them, we can try and figure out their percolation thresholds, and when you do that, and you plot these points, they're unfortunately all worse than the 2D surface codes. So this is kind of disappointing until you realize that for whatever reason, the people who compile these lists of geometries on Wikipedia, they're all geometry people. And those geometry people are really only interested in convex polyhedra. I don't really know why that is, but it is the case that on Wikipedia, those are pretty much exclusively made up of convex shapes. But there's a whole world out there of non-convex geometry. And if we remember what it is that we're actually trying to do with this state, it's just using this geometry to define a structure of entanglement. So we don't care whether or not this thing is bendy or curved or weirdly shaped, because the entanglement can be configured however we like. And so here is the fact that I found extremely surprising when I realized this, that there's actually many self-dual geometries in 3D, so self-dual cell complexes, if you go beyond these convex geometries. So cubic is really the only self-dual if you're restricting yourself to convex geometries, but in the non-convex space, there's many, and in fact, whole families of them. So let me give you one example. Here it is. This is the diamond cell complex. So the thing is based on the diamond lattice, but the lattice itself is not enough. The key thing is that you have to be able to define faces and cells on top of that lattice so that the thing is self-dual. And it turns out with this you can do that. So here's one cell represented. It's got 4 hexagonal faces that are arranged in such a way that the vertex at the middle also has degree 4. And you can set these things out so that actually every vertex is identical, every bond is identical, and the thing is self-dual. And the important thing about it is that it has a valence of 4, which is 2 lower than what we started out with the cubic lattice. So the valence has come down, and the erasure threshold goes up to 39% in both the primal and the dual, which moves it straight up into that green region. So I guess in some sense we succeeded. We found something which, on this metric, really outperforms the cubic lattice. It's self-dual, and it has a higher threshold against erasure. You can have a look at what that structure looks like. So it's got these kind of hexagonal faces. So in some sense, it looks a bit like the hexagonal surface code, at least on the face. You can certainly think of it as like on one of the faces is a 2D hexagonal surface code. But there's no way of compressing it or squashing it so that it ends up in these layers. So we can't really interpret it in that way. And maybe there are other ways to think about this, but here is one. This thing is still a channel, and it's a channel which allows us to move a surface code through it, so we can put it in at one end and get it out of the other end. But somehow this structure is allowing us to take a hexagonal primal part and a hexagonal dual part and take them through the same channel, even though they're not dual to one another. So we can create a 3D structure which is allowing us to get a duality between things which can never be dual to one another in 2D. So we can go back to this picture, and there are more examples that go up along this line. So, you know, there's a kind of thing that looks with these octagonal faces on a cubic lattice, and then this thing called the trimond lattice, which has a valence of 3 and gets an erasure threshold of 55%. So that's the lowest valence and the highest erasure threshold that you could get with something which has a uniform degree of syndrome graph. So you may look at this and feel a bit disturbed by those numbers, and certainly we did when we first saw it, because it's above 50%. And probably the intuition is, well, how can we have an erasure threshold which is above 50%? And I think that's a good question to ask. But the reason that we find that a kind of weird, unpalatable thing at first is because we're very used to thinking about codes. So error-correcting codes certainly cannot have an erasure threshold of more than 50%. That's as high as you can get. But a fault-tolerant channel is not a code. A fault-tolerant channel can be doing one specific operation, which doesn't necessarily allow anyone who had access to less than 50% of the qubits to choose what they do to it. So it's certainly possible that two people could get access to 45% of the qubits and reconstruct the fault-tolerant channel, but that doesn't allow them to violate no cloning. So this actually leads to a kind of interesting distinction. And I haven't really said much about the way the different ways that you can do computation in this measurement-based setting on some resource state. But this feature really means that there are two very different regimes that depend on how you're actually going about implementing computation. So if it's the case that we have a fixed resource state and you're implementing computation by doing measurement, so this is something you can do that's been proposed originally by Rausendorf and others in these seminal papers. You can take a single state and you can get to a universal gate set just by doing a different set of measurements on that state. In that regime, you cannot have a threshold of more than 50% overall, because you're able to choose what operations you're doing on the state. But there's another possibility, which is that rather than doing the measurements on the state, you actually prepare the state that you would have had if you had done those measurements, or you prepare a state that at least is topologically equivalent. And we can always do this, that instead of doing the measurements directly, you can prepare a different state. And if you have that ability to change the topology of the state in order to do logic, then you're not restricted with what threshold you have, because you can always be preparing a channel which is specific to that gate. So really, these things are very different. I mean, a way to think of that for the surface code, I mean, in this example in particular, is that we have a very high threshold in the bulk, but when you try and create boundaries, the threshold is very poor. And there's another regime where you can create boundaries with very high fidelity, and the bulk is very poor, and these are these two different regimes. Okay. So we now have a bunch of examples. They have these very nice erasure thresholds. But now, just like in the last bit, I want to talk about how this maybe maps to some real systems. So we care about Pauli's, we care about circuits, how are you actually going to build the things, we care about gates. And I think it's very difficult to say things concretely in this area, because everything is so dependent on the technology and the way you're actually doing things, but I'll try and give some examples. Okay. So the first thing is just the phenomenological Pauli threshold. So I said erasure is a very good proxy for Pauli without much justification, but these are the results, and it does indeed suggest that it's a good proxy. So what you see is that as you go down this progression, the things which have a higher erasure threshold also have a higher threshold against Pauli error. So these things are phenomenological thresholds, which you can compare to the case that every qubit gets a bit flip and every measurement outcome gets a flip. It's also just worth noting that these calculations were performed with the union fine decoder, which has a slightly lower threshold than perfect matching, which are kind of indicated in that first bar. So probably all these other numbers can also go up a bit if you use a better decoder. Okay, so what you should think when you see this is, yeah, those phenomenological error rates are really high. But as I look at the states along the bottom, they're getting more and more complicated. And I can confirm that they got more and more difficult to draw as we went to the right. This one on the right has degree 10 vertices. The syndrome graph is 3-valent, but the cluster state on top of it, which is telling you how many gates does every qubit have to go through, that goes up to 10. And generally, we don't like highway operators. They introduce more error. And so we really have to ask about the trade-off of those things, and is there actually still any advantage? And answering that question is very dependent on what the actual error model is, and it's actually going to change depending on how you vary these different settings. I think we care about exactly what are the primitive operations that you have access to. It's going to change dependent on what actual gates you can do. It depends on the bias in the gates, and we've heard a bit about that already this week, about the measurement errors, about correlations, also about exactly how you set up your circuits. There's many modifications that you can make to how you organize things to make things perform better, and all of these things are going to change the answer. So let me just talk through one or a couple of examples of that to give some initial idea of what the performance might be. So here is a circuit representation of that diamond lattice. This is a circuit representation. This is kind of the first thing that I thought of. Kind of interesting, so it looks quite like a hexagonal code, at least in the first layer it looks exactly like that. And then it goes through some kind of weird thing where the checks are actually happening between multiple different layers. And then again, it looks a bit like a hexagonal code, but offset on a different set of qubits. And then we have another one of these offset rounds, and then it gets back to the beginning. So I don't really know how to interpret that. I think it's an interesting question if there's some interpretation of what that actually means at the level of the code, whether you can think of it as some kind of like gauge fixing or shuffling around of the code or something. But anyway, so there's a possible circuit. This thing has 3 primitives, so it uses preparation in X, it uses a control phase gate, and a measurement in the X basis. So it's basically just a replication of that cluster state picture. So here's some error model. I'm going to treat the preparation in the plus state as ideal, take the measurement in the X basis as being flipped with some probability, and then take some standard model for a Pauli error that follows the CZ gate. And there are different models, and the distribution of the errors amongst those different terms is extremely important, and it's going to affect the results a lot. So the standard toy model, I guess, is this unbiased one where all of these Pauli terms happen with equal probability. And a fully biased one is the one where we only have the Z-type terms. We've actually heard from various people this week, from Shruti and others, that this is actually physically reasonable, perhaps in certain experimental settings. And there's also, I should highlight, been a whole bunch of work on this previously that look at these bias models. And so there was this first paper from Alaferis and Preskel who showed that if you have this bias, you can basically exploit encoding on the state to improve the threshold in these certain regimes. And there's been some other works that have shown kind of similar things with these biased gate error models. These numbers probably shouldn't be compared directly against one another because they're different numbers, but a bunch of people have seen a bunch of improvements. All of these results are based off the fact that the increasing stabilizer weight becomes more favorable if you're biased towards Z errors, because that's the case where all your errors commute through your gates and things aren't spreading around so much. If you're more dominated by bit flip type error, then things become worse, they get spread around, you probably want to have smaller weight checks. There's also a bunch of, there's other work on bias noise, this and some other papers which we're going to hear about later today. This is a slightly different regime where you have these Y-type errors, so things that are kind of show up in both the primal and the dual. Okay, so we can look at some results. If we take these bias gates and have no measurement error, and we compare the way these things perform, the advantage has diminished quite a lot compared to what we saw in just the phenomenological error, but it's still there for these gates. And what you're seeing is that we go up, these things compare differently because they have maybe different numbers of gates, but we're still seeing roughly a factor of 2 advantage there. We can add measurement error. That actually makes things better. You get a stronger advantage when you have a measurement error, because you can think of a measurement error as basically being another type of dephasing in this setting. And then we can add a bunch more measurement error, and this is the regime where you get the strongest advantage. So if we increase the measurement error to be 10 times higher than the gate error, then you see very significant improvement with these schemes, and you have much more motivation to have high weight parity checks if you have low gate error and high measurement error. Okay, so these results, I think, show that this can be competitive, at least with other schemes. And I think it also just highlights that the answer to which one is going to be the best is very dependent on exactly what the gate error model is and exactly how you set up the circuits. And I think there's probably a lot more that can be done on figuring out better ways of building them, because this is really just the first thing you would think of. And I know there's a ton of tricks that isn't something that I've actually spent much time doing, but many people have, about better ways of extracting this information in a fault-tolerant way when you have these bigger parity checks. Okay, so let me just sum up then. So I guess the main thing that I want to get across is that fault tolerance is the thing that we're actually after if what we're doing is trying to do quantum computation. What we want is to build these fault-tolerant channels. And starting with a code and building off it is one way to get there, but there are other ways to get there. There are other ways to construct these fault-tolerant channels, and I've talked about one of them. And this seems like it opens up a bunch of possibilities that are very hard to think about if you're just starting from a 2D code. So that example that I showed the circuit, I don't know how you would come up with that circuit if you're trying to think about it starting from the point of a code. So maybe this way of thinking can open up more possibilities for constructing fault-tolerant schemes. The second thing, which is pretty interesting, is that self-duality isn't limited to this one example of the square surface code, and actually there are a bunch of other examples where you can maintain this property of the balance between primal and dual. Maybe there are many other examples, I don't know. These are just the ones that we found. Was not part of any exhaustive search, it was just the examples that we found by some method of modifying the original lattice. And so maybe there are others that really have even better performance. And these things, even when you put very realistic noise onto them, still maintain some of that advantage and threshold. And it changes depending on the regime that you're in. So it's certainly something which isn't just a kind of interesting feature, it's something which maybe is really useful for real computation. And then there are obviously a ton of open questions here, and I think, yeah, I'd be very happy to talk with anyone who's interested about this afterwards. I think this idea of non-foliation I've talked about in the case of the surface code, but it applies in other cases. Should also highlight that this paper from Hector Bombin, which Ben talked a bunch about yesterday, which shows that you can do this transversal T-gate in 2D, is kind of built off the same idea that you can get to fault tolerance in a way that isn't foliated, and that was the same scheme that you used there. And there it wasn't about threshold, but it showed that you could get an ability to do logic in a way that you couldn't when you started by thinking about the 2D case. And what other ways are there of getting to non-foliated schemes for fault tolerance? Maybe there are many others. Maybe these can be applied to other codes. I think that's an interesting question. Be interesting to know what the optimal thresholds are for these things, and if there's any other geometries with better thresholds, better ways of constructing them. And yeah, this thing I alluded to, that is there a way of understanding what those things actually mean at the code level? Maybe that can open up some more intuition about other ways of improving the thresholds of fault-tolerant schemes. So that's all I had to say, and yeah, happy to take any questions. Thanks.
So are there any questions?
Okay, so I have a bunch of questions, but maybe I'll just pick one. So so if you make the normal 3D surface code on the cubic lattice, you obviously get one kind of defect being points and one is lines. Do you know what happens if you use one of your self-dual geometries instead and make like a regular 3D surface code construction?
Oh, I see. So actually building a 3D code on top of that geometry.
Yeah.
I mean, so it would give the same, you'd still have like the two different types. You'd have the plane-like one and the string-like one. But I mean, I presume that could, so I mean, the thing depends on the percolation threshold. So maybe that does improve the threshold. I'd have to think about how those things work. But so they go counter to each other. So when you improve the percolation threshold of a string, you make the 2D percolation of the surface worse. So I guess my guess would be you'd be balancing out between the two things. You'd make the 1D one better and the 2D one worse, bringing them closer together.
Thanks for your talk. It was great.
ask you a question about something I mentioned to you at the side the other day. There's a 4-dimensional regular polytope, this so-called hyperdiamond. It's the unique one that is self-dual and not a simplex or a polygon. And you might imagine that just like you can use 2D codes and sort of sweep through a 3D space, you could use 3D codes and sweep through this 4-dimensional space and maybe gather some of the nice properties like self-correction or something like that, or mimic it to some degree with such a sweeping through that. Have you had an opportunity to look at 4-dimensional generalizations of this kind of idea here?
Yeah, that's an interesting question. So yeah, I have no idea about the specific geometry that you asked about. If you take a 3D structure and sweep through 4D space, you have the same limitations that you do with the 3D code, which is that you have a percolation threshold that's like better in one direction and worse in the other. And the thing is that percolation thresholds, even for something which is 3 valence, say, you have a worse percolation threshold in the higher dimension for the same valence of graph. You would have to go to 3 plus 1. 4 plus 1, you'd have to start with the 3-dimensional thing, the 4-dimensional thing, and sweep it to get a 5-dimensional thing to get the advantages of self-correction to be building the equivalent thing. 4 dimensions seems maybe a bit challenging for something to be constructing. Maybe not with photons, but yeah, it's an interesting question. And I certainly wonder whether there are, I mean, that's the naive thing. So if you just construct the cluster state to be replicating the behaviors that you would have with the code, that's what happens. But maybe there are other ways to think about it in this way. I don't know. I think it's very interesting.
There's one more question right here. That'll probably be the last one.
Hi. Thanks for the talk. At some point you mentioned that all these percolation thresholds are like bulk percolation threshold, but then that if you added boundaries, things could change a little bit. So I didn't quite get what you meant.
Yeah, so the threshold in the bulk is determined by the bond percolation threshold like on the syndrome graph. But if you want to create a boundary with measurement, then it's a different type of percolation problem. The fact that it's percolation is because you measure everything in the x basis, and this creates a certain kind of syndrome structure. At the boundary, when you measure z, you're essentially solving the complementary problem. So the thing you have to do is have the percolation of a surface to be able to create the boundary. And that means that, yeah, you have 1 minus the threshold of the other percolation. So it's actually just exactly the 2 things have to sum to 1 for the case of the surface code.
So for this like very high threshold, then you wouldn't want to measure ever your qubits, or?
Yeah, so in the case that you build like the trimond one, you have a threshold of 55% in the bulk. If you try to create boundary, you'd have a threshold of 45%. But the thing is, you don't actually need to create the boundary via measurement. I can create the boundary by constructing a state that has boundaries to start with, and then the threshold is given by the higher one.
Thank you.
All right, so let's thank Naomi again.